In de Broglie's hypothesis, a moving particle always has a wave associated with it, and the motion of the particle is guided by that wave. The electrons, protons, atoms, and molecules, when in motion, have some type of wave motion associated with them that is called as a matter waves. Matter waves can propagate in vacuum, not mechanical waves. Matter waves are associated with motion of neutral bodies. It's not electromagnetic waves. So as shown in this diagram, we have the matter wave, that is the de Broglie's wave, and the wavelength we can calculate lambda is equal to h upon p, where lambda is a wavelength, h is a Planck's constant, and p is a momentum. The representation of the matter wave or the de Broglie wave is shown in this animated figure. In 1924, Louis de Broglie used Einstein's equation E is equal to mc square and incorporated it with Planck's equation. This brought together the relationship of the mass of a photon and speed of light with a photon energy. Einstein's equation E is equal to mc square, where m is a mass of proton and c is the speed of the light, combined with Planck's equation E is equal to h nu. So therefore, the simplification of these two equations is E is equal to mc square and E is equal to h nu gives mc square is equal to h nu, which gives mc is equal to h nu upon c. Therefore, mc is equal to p, where p is a momentum. Since wavelength is speed of light upon frequency, so we can write lambda is equal to c upon f. Whereas momentum is equivalent to p is equal to h nu upon c, so we can write p is equal to h upon lambda. In order for this equation to apply for the purpose of material particle, that is electron, de Broglie changed the equation to its equivalent. So therefore, p is equal to h upon lambda changed to lambda is equal to h upon p. So p is a momentum. So momentum is nothing but the mass into velocity. So lambda is equal to h upon mv, where p is the product of mass of the particle and the velocity. So therefore, lambda is equal to h upon mv demonstrate that particles have wave-like properties are known by the integration of wavelength lambda and Planck's constant h and momentum of the particle, that is p, is equal to mv. This equation is known as the de Broglie's wavelength. He reasoned that if things that acted like waves had particle characteristics, then it should work and vice versa. Therefore, things that behave like particles should also have wave characteristics. He coined the term matter waves to describe waves that involves material particles such as electrons. We have seen the de Broglie's wavelength equation, that is lambda is equal to h upon p or lambda is equal to h upon mv. This is a very general form. So let's see the de Broglie wavelength of a particle in terms of its kinetic energy. Consider a particle of mass m, small m, moving with a velocity v, small v. Its momentum is, then we can write small p is equal to small m into small v, that is p is equal to mv. And the de Broglie wavelength of matter waves associated with is given by lambda is equal to h upon p, that is equal to h upon mv. Let's say this is equation number 1. So the associated kinetic energy of the particle is given by E is equal to half mv square. This is a very general equation, as you know that. So by rearranging this equation, we can write E is equal to 1 upon 2m into m square v square. So multiplying and dividing by m, we have this equation. So E is equal to 1 upon 2m m into m square v square. So this is equation number 2. So as p is equal to mv, rearranging this equation, we can write E is equal to p square upon 2m, or simply p square is equal to 2m capital E, or p is equal to under root of 2me. So this is equation number 3. Putting the value of p momentum in the equation of the matter wave, we can write equation number 1 as lambda is equal to h upon p is equal to h upon under root of 2me. So this equation number 4, the above equation gives the de Broglie wavelength of a particle of mass m and kinetic energy E. This equation is true for any particle irrespective of its charge or the mass. Now let's see the de Broglie wavelength of an electron or proton accelerated by some potential difference. Now consider if a charged particle such as electron of mass m0 is accelerated by potential difference capital V, that is volts, then the kinetic energy of this particle, that is electron, is given by kinetic energy is equal to E into capital V, where small e is the charge on electron, which is half m0 v square is equal to EV. So this is the equation number 1. So we just combine the equation of kinetic energy and its charge and the potential difference. Hence we can write this equation number 1 as m0 square v square is equal to 2m0 small e into capital V. Therefore m0 v is equal to under root of twice m0 small e into capital V. So this is equation number 2. The de Broglie wavelength associated with the electron can be written as, the general form of the equation is lambda is equal to h upon p. So this we can write lambda is equal to h upon m0 v. So this is equation number 3. So from equation number 2 and 3 we can write lambda is equal to h upon under root of twice m0 e into capital V. So this is the equation number 4. So from equation number 4, this equation is for an electron, that is m0 e is equal to 1.9 into 10 raised to minus 31 kilogram. This is the mass of the electron. Hence this is the equation from 4. We can write lambda is equal to 12.26 upon under root of capital V in angstrom unit. So capital V is a potential difference. So for the proton, its mass m0 p is equal to 1.673 into 10 raised to minus 27 kilogram. So hence equation number 4 we can write for the proton lambda is equal to 0.286 upon under root of capital V, that is potential difference in angstrom unit. So these are the two values for the de Broglie's wavelength for electron and the proton. Now let's see the properties of matter waves. Matter waves are different than electromagnetic waves associated with the particle. That is, matter waves are not electromagnetic waves. Hence lambda is independent of charge of particle. Therefore we can write the wavelength of the matter wave as we have discussed before. Lambda is equal to h upon mv. Wavelength is inversely proportional to the mass of the particle. So lambda is inversely proportional to m, which gives when the mass is small, that is the lighter particle, then its wavelength is large. Velocity of matter waves depends on the velocity of particle generating it. Therefore wavelength is inversely proportional to the velocity of the particle. So therefore we can write lambda is inversely proportional to the v, where v is the velocity. If the velocity of the particle is less, then lambda is large. So therefore if velocity is infinity, then lambda is equal to 0. So finite velocity for matter waves, and if velocity is 0, it gives the lambda is infinity. So finite velocity for the matter waves. Hence matter wave spread out in space and not localized at a point, which introduces the uncertainty in position of the particle. Hence matter waves are related with the probability of finding the particle. That is, matter waves are not mechanical waves. The properties of matter waves can be explained as follows. Matter waves are produced by the motion of the particles and are independent of the charge. Hence they are neither electromagnetic nor acoustic waves. They can travel through vacuum and do not require any material medium for their propagation. The smaller the velocity of the particle, the longer is the wavelength of the matter waves associated with it. The lighter the particle, the longer is the wavelength of the matter wave associated with it. The velocity of matter waves depends on the velocity of material particle and is not a constant quantity. The velocity of matter waves is greater than the velocity of light. They exhibit diffraction phenomena as any other waves. So all these properties are very important to understand the behavior of matter waves.